Hi, Robin here. This is 1.4.3, this is the Boolean algebra section, but we're actually going to look at the full adders and half adders. When we're carrying out binary calculations, and I'm sure you've maybe done this in class, but we can do this in a theoretical sense using a pen and paper, and we would follow a set number of rules. So 0 plus 0 would give us 0, 0 plus 1 would give us 1, 1 plus 0 would give us 1 as well, and then 1 plus 1 would give us 0 with a carry of 1. The carry is really important because what that means is it goes into the next part of the calculation and allows us to do more than one bit of addition at the same time. Ideally, therefore, what we would like to be able to do is, rather than just doing this on pen and paper, is to get the computer to do this for us. When we look at the table here, you can see that we've got the 0 plus 0 is giving us 0 and 0. And again, the 0 and 1 is giving us the 1 and the 0. So the S column here is the sum, and the C column here is the carry. Ideally, we would therefore have some electrical gates that would match this, and this is the case. So as you can see here, the XOR gate has a truth table which matches the S column, and therefore we can use an XOR gate to replicate addition in this way. Again, the AND gate has a truth table that has the same outputs as the carry. So in other words, a combination of an XOR gate and an AND gate will give us our binary calculation that we want, and therefore the computer is doing it for us. Therefore we combine them like this, where the A and the B are the two different values being added together. Going into the XOR gate will give us the S value, going through the AND gate will give us therefore the carry value. What we can do with this is create circuits that mimic the calculation and therefore does it on our behalf. The only thing to mention here is that this will only do it for one bit. It doesn't have the ability to do any more than that. Therefore we need a solution to that. We call this a full adder. A full adder starts off with our inputs of A, B with the C in. You can see it's just the same as before, where we've got our XOR gate and we've got our AND gate. But then the reason we call it a full adder is because it actually combines two half adders together. So that we've got the blue half and then we've got the sort of red colour half. You can see that the A and the B going through the XOR gate goes through another XOR gate to give us our sum value. And what it's doing now is it's taking in a C value, in other words, the carry from the previous calculation. What we then need to do with this is use an OR gate here to create a C out value, which will be the carry that goes into the following calculation after that. In other words, we've got the ability therefore to keep putting this circuit together with other circuits, and we therefore can create really long binary number calculations. Here you can see we've got a table to show the truth table of this, so therefore when we include the C in, we get the C out values that we need, and all of these therefore give us the same mimic that we would have when we do this with paper. So in other words, when we have a 1 plus 1 plus 1, it gives us a 1 and a carry of 1. Whereas if we do 1 plus 1 with a carry of 0, it just gives us a carry and we get a sum value of 0. And that matches. So therefore, in other words, this has given us the ability to perform binary calculations. What we can do is simplify this into a layout like this. You could argue that this actually doesn't help us much because we don't know that now what the gates are inside. But what it does do is it means we can represent and show this in an easier way. And therefore, if we were asked to draw this in an exam, we would just simply draw out the two half adders together with the OR gate, and then that would be appropriate for an answer. We are doing a computer science A-level rather than doing an electronics A-level, so hence why this would be deemed appropriate. What we can also do with this is show this again within the table, and again so you can see how we've got our C1 and C2 values in the diagram in the top right hand corner, and you can see how again they would work within the truth table, and you can sort of see how that would therefore give us all of the combinations that we need. We can simplify this even further, so we can have a full adder. What we've now got here is we've got our sum coming out, showing that particular bit's value. We've got our A and B inputs, and then we've got the C in coming from the previous bit, and we've got the C out, which will lead us into the next one. This is useful because what we can do now is concatenate full adders together. In others, we can replicate longer binary numbers, and we can do this visually. One thing to remember is that a binary number goes from right to left, doesn't it, in the way it's written, the way it goes sort of up in value. So again, we would want to show the concatenation going again in that direction. So in other words, the arrow coming out here is going in that direction, and it's going in that direction from right to left. Here you can see now that as we've got our, like I said, our direction going across, you can see that we've got our binary number. So as we've got 0, 1, 0, 1 of a 5 plus 9 of 1, 0, 0, 1. And therefore by adding that together, we then get our output here of 1110, which is then 14, which is the correct answer. One thing to notice with this, and if you imagine you're manufacturing this in a factory, it's much easier to make this component and then just replicate it again and again. What this does, however, is it leaves us with a carry at the end. In other words, if electricity is coming out of this, we have what's called an overflow, and that's where that comes from. You may have heard that or not fully understood why it existed. Okay, so what you can see here is a half adder, and therefore what we've got then is the A and the B inputs. So if we were going to do a sum such as 1 plus 0, what we can see is electricity going into the circuit from the 1. It goes through the XOR gate. It therefore gives us an output of 1. The B has an input of 0. Because it's XOR, it'll be one or the other, and therefore gives us the output. And because the B is off, we therefore have no other output. In binary, 1 plus 1 is 0 carry 1, and therefore if we turn them both on, 1 plus 1 are both on, we now have the 0 of the sum and then the carry that can be then be used. Okay, so what we can see here is a full adder circuit using the XOR and an AND gate. So if we have two inputs, A and B, in other words, we're going to add 1 to 0. When we have 1 plus 0, that is 1. And therefore you can see that as the electricity goes through the XOR gate, and it also goes through the AND gate doesn't do anything because it's got no other secondary input, but an XOR gate allows electricity to go through. Again, it goes down to the second AND gate, nothing happens, but it does allow it to go through the second XOR gate of the sort of second part of the half adder, and therefore gives us a sum output. If I then turn on the B instead, you can see the same things happened. So electricity is not getting through the AND gates, but is going through the XOR gate, and therefore gives us an output of 1. So in other words, 1 plus 0 is 1, or 0 plus 1 is also 1. If I turn them both on now, we've now got 1 plus 1. In binary, therefore, 1 plus 1 is 0, carry 1. And as you can see, we've got them both going into the XOR gate, and therefore that's not going through, and therefore the electricity is not reaching the sum, and therefore we don't have an output. So in other words, 1 plus 1 is 0. But what does happen is it goes through the AND gate, and that gives us, via the OR gate, our carry, which would then go into the next part of the circuit. So if we were to have multiples of these up going in, we would therefore have a carry value that would come in here into this C value. If I then turn that on, so we're imagining we've got a carry coming from another circuit, we've now got 1 plus 1 plus 1, which is 1 carry 1, and therefore you can see that both the sum and the carry are both on. Okay, so what we've got here is a full adder, but using a NAND gate. So as you can see, there is repeated NAND gates throughout this circuit, and that's incredibly useful because if you think about it, if you only have to make one type of gate, you can therefore replicate that, manufacture that much, much quicker, but still achieve the goals that you need to achieve. So I'm just going to demonstrate this for you. If you imagine we've got two inputs, A and B, therefore if A is 1, and then we're going to add this together to B being 0, 1 plus 0 would be 1, wouldn't it? And therefore the sum is on, and we can see that. If I then was to turn A off, and therefore again turn B on, again we would have 1 plus 0, and therefore the sum would again be 1. If I turn both A and B on, we then have 1 plus 1, which is 0 carry 1. And as you can see, the sum is off, but the carry, the C value, has come on. If you imagine this was part of a circuit where it had a previous input, and that previous input was on, we would then have 1 plus 1 plus 1, which is 1 carry 1. In other words, the sum is on and the carry is on. Okay, so this is a 2-bit ripple carry adder. Ripple because the electricity effectively is rippling across different circuits. What you can see here is I've got an input for A and B. So just like before, if A is on, we get a sum value come out. So therefore 1 plus 0 is 1. If both of them are on, we've got 1 and 1 is 0 with a carry. So you can see that the sum has given us a 0. And then we've got a carry. In other words, the carry is going into the next circuit. And as you can see, that gives us an output of sum, which would be true, wouldn't it? We'd have 1 plus 0 in there, and that would give us 1 coming out of it. So in effect, we've been able to create a circuit that represents that action. But what we can also do now is, because we would have multiple bits running together, so in other words, we could have something like 1 1 plus 1 0 as a simple calculation. What we can now do is have a second input of 1 on. That takes into account now the sum, which gives us the carry that's coming through, which therefore gives us 1 and 1 is 0 with a carry 1. And again, if the B is on, we now get the sum coming out of there, as well as the carry going through into the next part of the circuit. So we're going to take this to the extreme, if you like, and show a 8-bit ripple carry adder. In other words, we can represent 8-bit calculations. So this is something I'm sure you've done many times in lessons where you've had to add two 8-bit numbers together. What we're able to do, therefore, is represent this in the circuit. So in other words, our A's would be the first number and our B's would be the second number. So in a way, I've got 1, 0, 0, 0, 0, 0, 0, 0, plus 0, 0, 0, 0, 0, 0, 0, which therefore gives me an output of just 1, doesn't it? And you can see that represented. Again, if I have 1 plus 1, that would give me 0, but it would then give me the carry going into the next part of the circuit. And therefore, if I now had 1, 1, 0, 0, 0, 0, 0, plus 1, 0, 0, 0, 0, 0, 0, what we'd actually get, therefore, would be an output of 0, 0, 1. And it's just representing and showing that. So in other words, each is going through. So what I'll do is I'll just put in a binary number such as 1111111 as we go through, and we've added that to another number. Let's kind of take this even further and do 8 ones plus 8 ones. What we've got here, and what's worth noticing, in the bottom right hand corner is the carry is on. And this is why we get an overflow. Because if you think about it, once you've got the circuit made to use the carry, you just repeat that same circuit. And therefore it's much easier to produce replicas of it again and again, isn't it? For as many calculations as you want, for any length of calculation. So if you imagine you're doing a 32-bit number, you just have 32 of these circuits going along. However, the last one includes the carry, but that carry doesn't go anywhere. In other words, that's an error, isn't it, at that point? So this is why we have to be aware of that and understand what that actually is. Okay, well, I just wanted to say thank you for watching. I really hope you found it useful and really hope you've learned something. Please do like and subscribe, and I'll hopefully see you again. Thanks a lot. Bye.